Thanks. I'll try not to bore you too much, and then keep the time so that we are on time with our fun part, just chat. But I'm going to plunge right in with introduction and an outline that I'm going to talk about. First, I want to talk a little bit about Pearson's treasure trove of probabilities distributions, tons of things that have been created before us. And then I'll talk a little bit about quantile functions. I call them the dark side of statistics. And then I'll introduce what we have done in quantile-based Bayesian inference, where the prior and likelihood can be defined by quantile function. I'll mention a little bit inversion of quantile functions, and at the end show an example of parametric quantile regression. That's the plan. So lots of distributions have been developed until now. This is just one big and confusing chart that is created by Lemis et al. Check out, it's a lot of distributions. Distribution system was originally proposed by Pearson and others, or rather discovered maybe, because it's so elegant and so nice. But it's pretty confusing to orient yourself in that space of probability distributions and all the interrelationship between them. So I kind of subset of these. Interestingly enough, lots of these distributions have been developed. They all have, of course, density functions, because that's how people think in terms of distributions, but only these distributions are possible to generate from. So it's kind of interesting that like you have a lot of distributions, but not all of them have ability to generate samples from them. And so my talk is kind of trying to address that conundrum. So conventional distributions are defined by CDF, where data is the first class citizen, because the f of x function is taking your data, which is x, ideally in real space, and maps it onto the probabilities, these u that live in 0-1 space. It's easy to do inference on x, on data, using the CDF-based distributions, because they are defined in terms of CDF, right? Equally plausible way, as Mr. Turkey has called it in 1965, is to define distribution via quantile function. Quantile function is the probability distribution, or the way to define it, where the probability is the first class citizen. So a quantile function is the function that maps the inverse, right? The u onto x. And so it's easy to generate synthetic data from that distribution. Quantile function is allowing you to sample. But the real-time data may be challenging to map, because you need to invert that function to find what the corresponding u would be for every observed data of x. So it's kind of, I call it a model-specific view of the world, because when you pick an observation, you don't know what u corresponds to it. It's just a data point, right? So you need to apply a model, and through that model, you'll see what the u that x might correspond to. It's like a little bit of a statistical goggles onto the world. So I'm going to talk about Bayesian inference with these quantile functions. So for given a random sample of y of size n, we can compute this sample of q of u. So for every sample in y, we get q of u1 and up to n, such that the u values are depth values. They are corresponding probabilities that correspond to those observations given parameter data. And therefore, our Bayesian inference model, this is the conventional model, can be transformed. Instead of underscore y, we would have underscore q, this sample of these quantile function converted u values. And then the likelihood term, where the q is now standing instead of y, is a product, again, of densities of these quantile functions. So it's density of quantile functions, a very strange kind of way-looking formula. And there's a term for it, density quantile function, which I unfortunately did not talk about in this slide. So I'll return a little bit to explain what that is. The whole idea of this Bayesian inference with quantile functions is based on this little Möbius loop, which is included in the paper that I'm kind of explaining today. You can download this Möbius loop. I should have printed and brought it, but it's a very nice little kind of paper-based tool that you can use to navigate through quantile function and distribution functions. So let's start with familiar f of y. The derivative of f of y is little f of y, and that's probability density function. You know that part. But on the inverse side, right? On the Möbius loop, it would be on the opposite side. There is also a quantile function which is inverse of CDF. That quantile function can also be derivated. You can take a derivative of it, and you'll end up with this quantile density function, the little q of u. And it turns out the f of y, the little f, and the little q are reciprocally related. They are not inverses of each other. They're just reciprocal. So if you take one over, you get the other one, right? And so that property allows you to really connect to something that would be equivalent of PDF without actually having PDF, because you can go through the other way to the same result. Numerically, it's the same result, but you arrive to it through derivative of the quantile function. So this is what, on this slide, the last term here is the product of the density quantile functions. I mean, to the power of -1 means that it's a reciprocal. This is, in fact, numerically a PDF, right? So it's based on the ideas developed by these fellows, and then we'll elaborate it a little bit more in our paper. So quantile-based likelihood then, since the likelihood is expressed in terms of these depths u of I, then the additional step is required in order to arrive at them. So they actually describe the data, but you need to get to those u of I. So there is a step of inverting a quantile function to find the depths u or underscore u. And inverting of quantile functions is a root finding step, basically. And it boils down to taking observation, let's say y, and then you subtract or somehow compare it to the q of u with parameter theta and try to minimize the difference until they're the same. And that process of minimizing the difference between the two terms is root finding of the function, right? So this is a target function which is plugged into root finder, and any bracketing root finder would be able to succeed. And the reason I mentioned bracketing, because in this case, the u term that you're trying to find lives on 0, 1. So if you are not bracketing, if you're not limiting the root to be found on 0, 1, you can try to find root elsewhere, and that doesn't make any sense because the probability is only valid for 0, 1 interval. The same trick can be also used for the prior. So kind of switching gears a little bit, there is a somewhat simpler formulation. So assume that the prior of theta can also be described by a distribution, right? That has a quantile function. So it's an invertible distribution that has a quantile function. So f of theta, let's say we have a hyperparameter here, is equal to v. So the q of v now is equal to theta. So those are just description of the prior. And then we can substitute these quantile values for the values of theta into the prior. This is our prior, f of theta given hyperparameter. And therefore, we also end up with quantile density, a density quantile function, the reciprocal of quantile density, that describes our prior now. So the prior is also now expressed in terms of these depths, but now it's v, not u. And this formulation is quantile-based, and it's a prior distribution of random variate v given hyperparameter corresponding to the parameter theta. So this is very similar, if you're not recognizing yet, this is very similar to inverse sampling, how people sample from all non-uniform distributions, because v is uniformly distributed, and then q of v will transform it to the space of parameter. So one thing to mention there is that the likelihood now, if you substitute this, drop into instead of theta, the likelihood now relies on the transformation, and therefore you need Jacobian. But Jacobian, nicely enough, is just an absolute quantile density function. So the density that is representing the prior plus the Jacobian kind of cancel each other out. So at the end of the day, the only thing that your Bayesian model will look like is likelihood with a quantile function transformation, and you get posterior. Of course, this is posterior of a random variate v, not of a theta parameter that you're interested in. But it's easy to get from here to back to theta by applying the quantile function as well. So that's how it looks. You only need quantile function in order to define a prior. You don't need density, and of course this random variate v, which comes for free in standards. So the likelihood, the application for these kind of weird formulations for likelihood is prior. and prior is that for likelihood, you can use distributions defined by non-invertible functions that only have quantile side, but not the density side. Let's say you may not have heard of many of these names, but GLD is a very popular distribution in the survival literature when they're trying reliability analysis and things like that. And Vakibi is distribution designed specifically for floods. So it's also a very weirdly shaped distribution that is not possible to reproduce in the density space. It's only in quantile function that is defined. Rajul is also a survival. GNH, GNK are very strange distributions, and others. So there are many distributions that have been developed that don't have an equivalent. They only have quantile function, but not the CDF. And as I will show today, regression quantile functions are possible. You can create a regression using the quantile function. For priors, any distribution with explicit quantile function, which is what you need to sample. So anything that is sampleable can be your prior. Basically, that's all I'm trying to say. Also including quantile parameterized distributions, that's I'm not going to talk about today, but there are some distributions that are super easy to construct directly from expert judgment that only require you quantile probability pairs. Unfortunately, they also define in terms of quantile function, not in terms of CDF. And those distributions are mapping directly to prior. So you elicit, and you don't need to fit any other functional form. These pairs will become your parameter. Or new distributions created using the rules. I include the link here. This is a super cool book that describes the consistent rules for arriving at new distributions when you need to. I'm going to kind of quickly skim over this. This is a little bit maybe overwhelming at this time of the day, but basically linear regression consists of or can be represented as a deterministic term and as a stochastic term. In deterministic term, in the simplest kind of example, you have an intercept and a slope and something of a random term that kind of varies from observation to observation. Then the error term, these epsilon, can be expressed through a quantile function as well. So now if we, instead of the error term, we drop in the quantile function, this S sub epsilon is a quantile function, then the whole regression turns out like this. I mean, the deterministic term is the same, but the error term is now kind of converted into, as we did, right, for many other things. You've seen this already. Substituted with an unknown depth U, given parameter, this is shape parameter theta, that allows you to represent it in quantile form. And none of this is much. The whole regression equation then can be expressed as some sort of location for the quantile function plus quantile function itself, where the location is describing deterministically the relationship between the variables, and scale parameters here before the quantile function is 1. And if you also include into the scale, if you also include dependence on the covariance, then the model can capture heteroscedasticity, which is what I'm going to show in a second. So the whole kind of challenge now becomes, how do we find this term U that would describe observations Y? Because we don't observe these U's, we only observe Y's, and they're somehow dependent on covariance as well. And in order to find them, we need to invert the quantile function. This is parametric quantile regression quantile function. Invert it to get to the depths U. Yeah, so here's an example of a car stopping data set where basically we're trying to predict stopping distance by speed. And from physics, this is known fact that the stopping distance is proportional to the square of the speed. And these are the priors defined for intercept and slope in that regression. The whole kind of idea, the whole kind of problem boils down to how do we describe that error term? The deterministic relationship is known. We have a stopping distance that is square of speed, so therefore speed is a square root of a distance. But the stochastic term can be kind of a little bit shaped up. We're using the quantile function. So what we expect in that relationship is that the error term, the residual, is likely to be heteroscedastic due to inertia. It doesn't matter whether your car, I mean, if you're moving at high speed, the inertia can cause the car to really slow down very slowly. So you'll have a big variance at higher values and relatively small variance of stopping speed and smaller values. It's also likely that the residual will be flatter than normal because the values can be very much spread, and also possibly skewed because you can't overcome physics. Basically, the residuals will be such that you can't stop faster than the most efficient car, but you can stop very inefficiently. So in one direction, the error term can be really expanding. So you start with something well-known, like a logistic quantile function. Here's, it's a difference between the logs, or log of u divided 1 minus u. And then you introduce the skewness parameter. So this introduction of skewness parameter is, according to Gilchrist rules, allows you to weigh in the two exponential tails of a distribution. Then you can also mix the uniform distribution to allow for thicker tails. So the way you would do it is you would add plus kappa, just a parameter that scales the uniform distribution, and the quantile function of uniform distribution, which is just a u. And all of this is wrapped into a scaling parameter, and there you have it. So this is like building block by block from a simple distribution up to a more complex distribution. A little bit overwhelming model, but it's not really too difficult because this is the main quantile function in here. This is what this quantile function describes a regression. Intercept plus slope times the covariate plus this error term, which is expressed by quantile function times the covariate because we want heteroscedasticity, and define a bunch of priors. Some of the priors are defined also indirectly. Let's say the FLD and FSLD are just these scale distributions that I showed you in a previous slide. And so these are quantile-based priors. And there are some R priors are density-based, exponential and beta and kappa. So this is just an example, kind of boils everything together into a single space. The results are posterior distributions of alpha and beta here are computed, of course, from the random variables that I showed, all converging pretty nicely, and you get a distribution. So this is for hypothetical outcome plot for 5th, 50th, and 95th quantile. You actually have, because this is expressed by quantile function, you can see at the uncertainty due to parameters for each quantile of the posterior. So these kind of plots are possible to derive at the end. One word, does it really work? So simulation-based calibration allows you to test if the model really recovers the parameters. And there are super cool papers, Modrak and others, and there are 2 other papers that describe how it works. But basically, you need a model, you need ability to generate data from the model, and the algorithm to fit the data to the model to the data using MCMC or HMC. I use Stan and 200 replications of 2,000 draws each shows you the rank of the true value of the parameter recovered in the posterior distribution. So if these ranks are for each one of the parameters, you get one of these plots. If these ranks are uniformly distributed and the confidence bands are shown by the blue, these are 95% simultaneous confidence credibility intervals. Then the parameters are truly properly recovered. Rank histograms, they're called. Or this is also can be represented by CDF, very nice paper that describes these kind of plots as well, some idea. So if it's uniformly distributed, then you have successfully recovered the parameters. So welcome to the quantile function artisan club, as I said. Make your own quantile function, and then you can do lots of things. It's based on the idea that the quantile function is something that you can, kind of cumulatively create dependent on your problem and, modify it in consistent manner until you get a model that you want. Don't start with a sheet of hairball of distributions. Start with your own problem and kind of build from it.